Good morning, everyone. The next tag is Maximal Torus action, Equivariant principal vendor, and Transverse Equivalence by Hiroaki Ishida from Kagoshima University.
Yes, thank you very much for the introduction. And I would like to thank the organizers, the Professor Ernesto Pescio, for giving me a chance to talk this very nice conference. Okay, okay, I'm a little bit nervous, so please forgive me. I would like to introduce maximal torus actions, and I would like to explain about classification of maximal torus actions. Complex manifold with maximal torus actions, and I would like to also explain about the relation with irrational funds. Okay. So first, let me introduce the notion of maximal torus actions. So we consider, let us consider manifold, smooth manifold equipped with torus actions. And the action of compact torus should be effective. And let us take a point in the manifold and consider the tangent space, its tangent space. This is a tangent faithful representation of the isotropy subgroup. And as a representation, this tangent space is decomposed into the two representations. One is so this is the subspace tangent to the orbit. This is trivial as representation of G sub x, and this is a normal subspace of this space. And this representation should be faithful because the whole representation is faithful. So we have an injective homomorphism from G sub x to the general linear group of this vector space. And let's consider the rank of the target D group. So since this is injective, we have the following inequality about the dimension of G sub x. So the dimension of isotropy subgroup should be less than or equal to the half of the dimension of this vector space, right? So this inequality can be simplified to the following inequality: the dimension of torus acting on manifold plus dimension of the isotropy subgroup is less than or equal to the dimension of the whole manifold. So here's, for example, if the manifold has a fixed point, then the dimension of torus cannot exceed the half of the dimension of manifold. Okay. So this and this inequality motivates me to define the notion of maximal torus action. Okay, so this is the definition of maximal torus action. So let M be a connected smooth manifold and G be a compact torus acting on M effectively. So the action of G on M is maximal if there exists a point in M such that the equality holds. The reason why I call this action maximal is the following. So if the action is maximal in this sense, then the group, then the torus G, so this G can be regarded as a subgroup of the group of diffeomorphism. This is maximal torus in. So the G can be regarded as a maximal subtorus in the group of diffeomorphisms. Okay, so this is a maximal torus action. And this is the main character of this talk. So we consider compact, connected, complex manifold equipped with maximal torus action, and this action should preserve the complex structure on M. And the purpose is the goals of this talk are following. So first, I would like to explain the classification of such manifold with torus action. And next, I would like to explain introduce Magdafan, which is this is so Magdafan is an irrational fan with certain information. And finally, I would like to explain about transverse toric geometry. So so this is a punchline. This is a punchline of this talk. Okay. First, let me show you several examples of maximal torus actions. So the first one is a trivial example. So let M be the compact complex torus, and G is also a compact complex torus, M itself. So this is Cn. So M is a Cn over gamma, and gamma is a lattice of Cn. So this is isomorphic to n-dimensional torus as real Lie groups. So for any point x in M, so we can check the equality. So namely, so isotopic subgroup of G sub x should be trivial because G is M is a Lie group. So dimension of G plus dimension G sub x is a dimension of whole manifold. The next one is also a trivial example in some sense. So let M be a compact toric manifold. So toric manifold means non-singular toric variety. Compact toric manifold of complex dimension n. And let G be the compact torus of the algebraic torus acting on the toric variety. Then for any fixed point, we can check the equality force, because so the isotopic subgroup should be G itself. So we have the equality. So compact toric manifold is an example of maximal torus action. In some sense, compass is also true. So this is a joint work with Yael Carson in Toronto University, in the University of Toronto. So let M be a compact complex manifold of complex dimension n. And suppose n-dimensional torus, real torus, acts on M effectively and preserves a complex structure. And we also assume that there is a fixed point. Then such manifold should be should be toric manifold. Okay. So this is example. So more complicated examples are Hopf surfaces. So we consider coordinate-wise action of sister 2 on C2 minus 0 by coordinate-wise multiplication. And let's take complex number whose absolute values are greater than 1, and consider subgroup of sister square generated by alpha 1, alpha 2. So gamma is isomorphic to the infinite cyclic group as groups. And the quotient space is called the Hopf surface. And the Hopf surface admits an action of this should be C star. Yeah, so the action of the quotient group. This quotient group contains three-dimensional compact torus as maximal compact torus. So, and we denote by G. We denote it by G. So for the point 1, 0 in the Hopf surface, we can see the equality. So we can see the isotopic subgroup at this X is one-dimensional torus. So 3 plus 1 is dimension of the Hopf surface. So more generally, all LVMB manifold admits a maximal torus action of torus. Okay. So LVM manifold has a natural torus action, and with respect to the such action, the action is maximal. Okay. So this is the simplest non-trivial example. Okay, now I'd like to explain about classification. To classify such manifold, we need invariance of. So we will assign invariant to such manifold. So to each manifold, we assign the following pair. So one is affine. So one is affine in the real algebra of the torus. The other one is a vector subspace. So this is a complex vector subspace in the complexified way. So to assign fun, to deduce a fun from MG, we need a characteristic submanifold. So let G prime be a one-dimensional subtorus of the D of G, and we consider, and then each connected component of fixed point set is a homomorphic submanifold of manifold of M. So with this understood, let me introduce the characteristic submanifold. A characteristic submanifold M prime of M is a complex codimension 1 submanifold, which is a connected component of the fixed point set for some subgroup, for some one-dimensional subgroup G prime. And this characteristic submanifold plays a role of toric divisor in toric variety. So using characteristic submanifold, we can obtain a fun in this vector space. Okay. So this is the fun for our manifold. So now we deduce the vector subspace Ha in the complexified gay. So since the torus action on M preserves the complex structure, this torus action extends to the holomorphic action of the algebraic torus GC on the manifold. So, but this complexified action is not effective in general. So, namely, isotropy global stabilizer could be non-trivial. So let H be the global stabilizers of this complexified action. Now this is a holomorphic subgroup of algebraic torus, and its the algebra can be written as this form, and this is a vector subspace of complexified gay. So this is a complex vector subspace H. Okay. So far we obtain fun and the pair of fun and vector subspace from manifold with maximal torus actions. And not every pair can appear. So namely, this pair is controlled by the following proposition. So first, so the delta, this fun should be non-singular fun with respect to the lattice in gay. So gay has a natural lattice kernel of the exponential map. So delta should be non-singular fun, and this is the second condition. Let P be the first pass projection. So the second condition is the image as the projection restricted to her is injective. And this is the second condition. And finally, let us consider the quotient map from G to the G over the image of her, image of her by P. And the third condition says that this quotient map sends the fun in here to a complete fun in this vector space. Okay. So the pair of fun. So far we deduce the pair of fun and vector subspace in complexified gay from manifold with maximal torus actions, and this pair is controlled by this proposition. So conversely, if the pair of fun and vector subspace satisfies the condition appeared in the proposition, then we can construct a compact complex manifold M with a maximal torus action as follows. By following way. So since delta is a non-singular fun, we have a toric variety associated with delta. And here is a vector subspace of Gacy. So the image of exponential map is a subgroup of the algebraic torus acting on the toric variety. So we consider the quotient space of toric variety by this subgroup. And we can see this quotient space is a compact complex manifold. Moreover, so the action of G on toric manifold, toric variety descends to the action of torus, action of G on the quotient manifold, which is maximal and preserves the complex structure. Okay. So the main theorem is the following. So far, so to each compact complex manifold with maximal transaction, we can assign a pair of Fan and vector subspace satisfying the certain conditions. And conversely, we can construct a compact complex manifold with a maximal transaction from the pair. So the main theorem says that so these correspondence are essentially one-to-one. So more precisely, the category of these categories are equivalent. I have remarks. So if we restrict our attention to toric manifolds in C1, in the category C1, and we restrict our attention to the case frame height 0 in C2, then this correspondence is nothing but the usual correspondence in toric geometry. So as is well known, non-singular complete toric variety. So there's a one-to-one correspondence between non-singular toric variety and non-singular complete toric variety and non-singular complete Fan. So this is a generalization of the correspondence. So, and I don't give a proof. I don't explain about proof of this theorem, but let me emphasize the difficulty. So the main difficulty is to show the isomorphism between this mysterious manifold and this concrete manifold. So namely, the existence of natural isomorphism is difficult. That is a difficult part. Okay. So we can classify all complex manifold with maximal transactions in terms of combinatorial objects. Okay, now let me introduce a marked Fan, which is a irrational Fan in some sense. So a marked Fan is a quadruple where so V tilde is a finite dimensional vector space, and gamma tilde is a finitely generated subgroup of this vector space that spans this vector space linearly. namely, gamma tilde is a quasi-lattice of V tilde. Delta tilde is a fan in this vector space, and each one cone in this fan is generated by an element of gamma tilde. And finally, lambda tilde is a function from the set of all one-dimensional cone in the fan to gamma tilde, to the quasi-lattice. And this function assigns generator to each one-dimensional cone. So we use the same terminology as usual fan. So namely, so the macro fan is, we say the macro fan is simplicial if the fan delta tilde is simplicial, and this macro fan is complete if the delta tilde is complete. So we can assign a complete simplicial macro fan to complex manifold with maximal transaction via the complete invariant and quotient map from G to G over P of R. So namely, so V tilde is this target vector space, and gamma tilde is an image of lattice in, So gamma tilde is an image of lattice by Q. And delta tilde is an image of this quotient map. So, and this is, and as I said, Q of delta is a complete fan in this vector space. So, and since each one-dimensional cone in delta has a natural generator, we also have a function by natural way. Okay. So we can assign complete simplicial macro fan from complex manifold with maximal transaction. Okay. And this is the second main theorem in this talk. So let us suppose we have complex manifold with two complex manifold with maximal transaction, and then so they have the same macro fans in if and only if they have a common equivariant principal band. So namely, there exists another complex manifold with maximal transaction and morphisms such that the map fy is a principal kernel alpha I bundle, and the kernel of alpha I is connected. Namely, this is a subtorus of G0. So, oh, sorry. So so there's an essentially one-to-one correspondence between the following classes. So there was one is a class consists of complex manifold with maximal Torus actions up to having same equivariant. The class so consists of complex manifold with maximal Torus action up to certain up to this equivalent relation, equivalence relation. This this is one-to-one correspondence. So there's a one-to-one correspondence between this class and the class consists of complete simple marked one up to isomorphism. Okay.
Just a little comment for the students. Let me just make a comment to connect this theorem, very nice theorem that you just explained,
Yeah.
to what I was explaining yesterday and what I will explain today. Yesterday, I explained that you could take a groupoid and making it fatter and then thinner. And this was called a homotopy or Morita equivalence between the group pole, and they would define the same stack.
Yeah.
This diagram is exactly that diagram, and what this proves is that M1G1 and M2G2 are define the same stack and the same quantum toric, stack. This diagram exactly gives you a Morita, a bibundle, what they call Hilsum Scandalis bibundle, that is exactly the structure of a Hilsum Scandalis bibundle that shows that the stack associated to M1G1 is the same, exactly the same stack associated to M2G2. So this equivalence relation that you write on the left at the bottom is exactly the equivalence relation to descend to the stack. So you are telling me that the stacks, our theorem is very related to yours, but we also consider certain kind of morphisms of stacks, not only the stacks themselves. But your equivalence relation is exactly equivalence relation for stacks. So this shows that the invariant object, the three things that you draw there in this theorem, are three atlases for the same quantum toric stack.
Yeah, thank you. Actually, I'm members to say that I'm not familiar with categories and so groupoids, and I'm not familiar with groupoids and stacks. So yeah, but thank you very much for the comment. Okay. Yeah. So yeah, maybe this is essentially the same as this theorem is essentially the same as you explained yesterday. Okay. Okay. So oops. Okay, now let me start to explain about transverse toric geometry. So we consider foliation on complex manifold. We consider very special foliation on complex manifold, so which is a so-called canonical foliation. So let me explain about canonical foliation and motivation for the canonical foliation. So let's consider a compact connected complex manifold. And let's take the maximal compact torus in the group of automorphisms of this manifold. Here we do not need to require the action to be manifold, to be maximal, but we take maximal maximal compact torus in this group, this Lie group. And let's consider one form such that which is closed, G invariant and non-negative. So non-negative means omega of xjx is greater than or equal to 0. But we do not require this quadratic form to be non-degenerate. So namely, this quadratic form may have kernel. So if the action on this manifold with two forms is Hamiltonian, then we can see that for any point x, the kernel of these two forms contains the following vector subspace. So this is namely this is a maximal complex subspace of the subspace tangent to the orbit. So kernel of these two forms should contain. So namely, this subspace is isotropic because this subspace is isotropic because all orbits of Hamiltonian torus action is isotropic. Okay, and this subspace doesn't depend on the two form. So this subspace depends only complex structure and the choice of maximal compact torus in the group of automorphisms. So we consider the distribution consists of the subspace. We can see that this distribution is integrable because there exists a subgroup of compact torus H prime. This H prime could be not closed, but anyway, there is a subspace subgroup H prime such that this distribution is actually coming from an action, local free action. So this distribution determine a foliation or determine a holomorphic foliation. The canonical foliation is the foliation given by this way. Okay, and so canonical foliation seems depending on the choice of maximal compact torus in the group of automorphisms, but actually we can say the following. So canonical foliation doesn't depend on the choice of a maximal compact torus in the group of automorphisms. So So this canonical foliation is intrinsic object for compact complex manifold. And canonical foliation is a lower bound of certain foliations. So if G invariant holomorphic foliation F on complex manifold admits a transverse scalar form and the first basic cohomology group vanishes, then such foliation should the subbundle corresponds to the foliation should contain the subbundle corresponds to the canonical foliation. So canonical foliation gives a non-trivial lower bound for the existence of certain transverse scalar form. So now we restrict our attention to the case when complex manifold with maximal torus actions. So suppose we have two complex manifold with maximal torus actions. So if they have a common equivalent principal bound, so namely, as I said, so if they have the same marked span, then we can say that these foliated manifolds are transversely equivalent. So namely, so here foliated manifolds are transversely equivalent if there exists another foliated manifold and holomorphic maps from M0 to Mi such that MFY is a surjective summation and preimage of each point is connected and preimage of each leaf is again a leaf of the whole total space. So this theorem, maybe this is a summary. So for the complex manifold with maximal torus actions, so having the same equivariant principal bundle is equivalent to the having the same marked fan. And by this theorem, if they have the same marked fan, so they are transversely equivalent. So we hope that we can describe all property of this foliated manifold by the combinatorial object, the complete simple marked fan. Okay. So for example, we can I have shown the following. So for complex manifold with maximal torus action with canonical foliation, the following statements are equivalent. So the first statement is, so there exists a transverse scalar form with respect to the canonical foliation. The second statement is the corresponding complete simple Markov is polytopic. So moreover, in this case, there exists a momentum map from M to Gesta such that this momentum map splits into the map to the dual space sits in a dual space. The dual of the space sits in this span and quotient map. And this phi tilde is the image of phi tilde. Image of M by phi tilde is a normal polytope of this Markov. So this is a generalization of the well-known fact in toric geometry. So here is another theorem. I do not explain the detail. Maybe Roman will talk about this in his talk. So actually, the basic homology of not only additive structure but also multiplicative structure of basic homology group, basic homology algebra can be described by the corresponding Markov. So more precisely, the basic homology algebra admits the almost same formula as non-singular complete toric variety. So, and here's this is also a generalization of the well-known fact in toric geometry. The set of basic homology classes of transverse scalar forms is open in the second basic homology group. So using this and basic Hodge decomposition, we can. Sorry. So use and as a corollary of this theorem, as a corollary of these theorems, we can see that the basic homology algebra. If this foliation is transversely scalar, then basic homology algebra of my manifold is generated by transverse scalar form. And using basic Hodge decomposition and this corollary, finally we can say that the basic Hodge numbers concentrate to the center as like non-singular complete toric variety. And recently, Roman and Professor Tarafanov showed that we can avoid the assumption from this transverse scalar from this corollary. Yes, so I'm so sorry for my bad English. So now I stop here.
Thank you very much. Any question? Thank you, Hiroaki, again.
Very nice talk. Thank you very much.
Yes, thank you.